scientists who believed their knowledge of chemistry gave them magical powers. They could summon fire, produce mystical potions. They even tried to turn metals into gold. Their magnificent feats enthralled kings and commoners alike, but they never revealed their secrets. By pushing the frontiers of science, modern chemists can perform equally impressive feats, and we're happy to tell you everything. Chemistry gives us an understanding of the world that the other sciences just don't. It's all about how one substance interacts with another to give us something new. Thank you. Take this Christmas tree here, for instance, a nice, solid structure. But watch what happens when I do this. Well, we certainly saw that a change took place there. There was a flash of light, I felt a blast of heat, the whoosh of sound, and then nothing was left at all. Trying to understand what happens when one thing changes into another is chemistry. My name is Dr. Peter Wathers, and I am a chemist. Now, the ancient Greeks thought that everything around them was made up of just 4 elements: air, water, earth, and fire. We see these here. In the next 3 lectures, we're going to look at what air, water, and earth are really made up of. But don't worry, there will be plenty of fire in all of the lectures. But this brings me to one important point. Please do not try these experiments at home. By understanding the elements around us, the modern building blocks of science, we need to look at the world in a different way. We need to see these elements through the eyes of a chemist. By understanding these elements, we can make better materials and better medicines for our future. We're going to start this first lecture looking at the air. Now, of course, this is something that we rarely think about, but without it, we'd all be dead. But just to show you that it really is here around us, pushing down on us, well, I've got a demonstration, but I'd like a volunteer from the audience, please. Right on the corner there, at the back. Yes, would you like to come down to the front, please? Okay, now, what's your name, please? Xavier, okay, right, so this is just a normal oil drum. It seems to be covered in a bit of rubbish at the moment, but anyway, if you hold this hammer, give it a good whack, Got a bit harder than that. Okay, it really is quite solid. Is it on the top as well, maybe? Okay, yeah, it's really solid. You think it's pretty solid? Okay, now watch what happens, though, when we take the air out of this drum. So at the moment, there is, of course, it's open at the top here. There's air inside, air outside. But we're going to put this pump on here. So we're now removing the air from this drum. Okay, and that's good. Now, I think you should just step it back. That's it. You stand over there. Yes, I'll stand over here. Okay, so we're removing the air from the inside of this drum. So to start off with, the air molecules were pushing against the drum, okay, but they're also pushing from the outside as well. So what do you think is going to happen then if we remove the air from inside? Any ideas? It will shrink. It will shrink. So do you think it's just going to gradually shrink up and get smaller? Yeah, well, that's a good idea. Yeah, that's what we think. Well, it doesn't seem to be doing very much at the moment, does it? So not a lot. Well, supposedly, these little air molecules are all pushing down. On this can here, we're taking the ones outside, we're taking them come and have a look then? So it is pretty solid. Do you feel that? It is very solid, isn't it? Okay, that was just the air. So we do forget about it, but it really is pushing down on us. There's quite a strong force. It's just like there's two full-grown men standing on your shoulders. But of course we don't notice it because we're used to it. We've adapted to it. Thank you very much. Give it a round of applause. That's great. But what about our tree? What happened to the tree? Well, what would the ancient Greeks have thought if they'd have seen that? What would they have made of this strange substance? Well, this, actually, the Greeks never saw. This is a substance called gun cotton. It was only discovered around 200 years ago. It's quite remarkable. The Greeks would have said that this is changing into fire and air. Maybe they would have said that this is made of fire and air. Or maybe they would have just said it's magic. Either way, they would be wrong. We now know that the air is much more complicated. It's a mixture of different components. And to show exactly what the air is made up of, again, I need another volunteer. Oh, there's a hand very quickly. I saw your hand. Right, yes, would you like to come down, please? Thank you. Okay, can I have a round of applause, please? Okay, your hand shot up very quickly there. Now, what's your name then, please?
Nadia.
Nadia, okay, excellent. Now, have you made air before? Having to think about that one. What do you think? Have you made air before, mixed it up, pure air? No. No, exactly. A bit of a strange thing. Of course, the Alchemists would never have done this either because they didn't know what was in the air. Do you know what's in the air?
No.
No? No? Oh, come on, have a guess. What, do you know any of the gases in the air? Very good, you see. Oxygen, you do know one of them. Do you know any other ones?
Carbon dioxide.
Carbon dioxide, exactly. So, we're going to see how much of the different gases are in air. Would you like to come over here? So these are all some gas cylinders that we've got here, and we've got the different proportions of the air you're going to add to this cylinder of water here. Okay, now then, the first one is the most common gas. It's not oxygen, it's not carbon dioxide. Does anyone else know? Do you want to shout it out? Nitrogen, yes, exactly. So the most common gas is nitrogen, and this is what we have here. So I'd like you to turn the tap for me, please, this tap here, and this is going to let some nitrogen in. Now we're aiming to get to this mark here. This is 78%, if we're going up to here as 100%, that would be 78% nitrogen. So, there's a lot of nitrogen in the air, isn't there? Okay, there's all this, look at this, you've got to stop it, just got to get this red mark here on the black mark. So you've got to get this just right. This is our nitrogen, and this is going to be 78%. Oh, okay, no, quick, stop, you've got stop, Robert. Oh, yeah, what a disaster. Oh, that's okay, look, there we are. Look, spot on, 78%, well done, that's fantastic, excellent. Okay, now then, the next ingredient, what's the next ingredient?
Nitrogen.
Oh, we've done the nitrogen, what's the next one? No, you like your carbon dioxide. It's oxygen, you're absolutely right, very important one. Right, so this is our oxygen. Okay, you're absolutely right there. So, right, you ready to go again? Not yet, yeah. Not yet. We've got to get 21%. Now, 21%, well, that takes us to about here, I think. Okay, that's 21%-ish. Yes, okay, that's 20%. So you're aiming for here, okay? Right, go on then. That's it. Very good. So there's quite a lot of oxygen as well. I can see the concentration now. That's what we need. Very good. Ah, look at that. Just about spot on again. Okay. Very good. Now then. Okay, now we come into the third most abundant gas. So far, we've got 78% nitrogen, we've got 21% oxygen, okay, and we've almost run out of everything else. There's only 1% left. Does anyone know the third most abundant gas? Now, you haven't mentioned this one yet. Does anyone know what it is? Want to shout it out? Oh, I had all sorts of different replies there, but it is, in fact, argon. I think some people said argon. Pat yourselves on the back there. It is argon. Right, this is a tricky one now, but you're getting very good. All right, argon. This is just 1%, so that's about there. Can you see that? I'll hold my finger here. About here. Here it is. Okay. Go on then. Go ahead. Whoops. Oh, nice. Wrong one. Yes, look, the audience are watching there. The argon one. That's it. Go on then. Give it a go. Brilliant. Oh, look at that. That is very good indeed. Now then. We're coming to your favourite gas. Which one's that one that's in here? Carbon dioxide, exactly. But there's not a lot of carbon dioxide. In fact, it's 0.037% carbon dioxide. Unless we did this 200 years ago, then it would have been quite a bit less. We've increased the amount. But anyway, so carbon dioxide, we just need a quick burst from that. So a quick burst from the carbon dioxide, that's it, that'll do. That's your carbon dioxide. Hardly any at all, but nonetheless, very important for us. All the plants need that. So that's our carbon dioxide. You still haven't made perfect air yet. We could breathe this, that would be okay, but there are some other gases. And these are some rather rare gases, but we've put all of these in this little syringe here. So would you like to just come and add your last bit of gas? So just push the plunger down and watch for the bubble. Oh, there it is. There we are. There, excellent. That's the last gases. This is neon, helium, krypton, and xenon. They make just a tiny, tiny proportion of the gas. You did very well there. Thank you very much. Give it a big round of applause. Okay, so now then we know that air isn't just one element, but it's a mixture of many. And before we look at these different elements from air in more detail, we want to see all of the elements that occur in nature. Now this is where you come in. You've got your cards here for different elements, so if you're a member of the periodic table, get ready. But to help us with this, would you please welcome, straight from the West End, the cast of the musical Loserville.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, radium, and all the protactinium, and indium, and gallium, and iodine, thorium, and thulium, and thallium. There's yttrium, and terbium, and cerium, rubidium, and boron, gadolinium, and iridium, and iridium, and strontium, and silicon, and silver, and samarium, and metals, lithium, beryllium, barium.
Barium, very good.
There's holmium, helium, and hafnium, and erbium, phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, molybdenum, and magnesium, dysprosium, and scandium, and cerium, and cesium,
and leprosy, athenium, and platinum, plutonium, palladium, rubidium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, mercurium.
There's sulfur, californium, and thermium, and helium, and also selenium, and sodium, nobelium, and argon, krypton, neon, and xenon, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These were the only ones they found back when this song was written. There are another 60 now, we'll show you where they're sitting.
Stand up as well. Excellent. You did very well, so my whole periodic table should be standing now. But would you please give a round of applause to the cast of Loserville? Thank you very much. Thank you for coming along. Thank you. Okay, well that was certainly chaotic, but you did fantastically well there. If you'd like to take your seats. Now, what about this sort of random order? You're springing up all over the place. Was it really a random order? Well, actually, it's not. There is some logic behind this, but to understand the logic, we need to look right into the heart of the atom. So atoms, as far as the chemists are concerned at least, are made up of three different particles. In the heart of the nucleus there are positively charged protons and neutral neutrons. And we can see these on the screen here. So the red ones are the protons, the blue ones are the neutrons. But then circling around we have these electrons. It's the protons and the neutrons that give an element its mass, make it quite heavy. So if you pick something up and say it's heavy, well that's because of the protons and neutrons. But it's these electrons that are right around the outside, and whenever you touch anything, what you're touching there is electrons. I bet you've never thought of this before, but if we shake hands, we're shaking electrons there. Okay, that's our electrons touching each other there. Anyway, right, so here we have our atom. Okay, we now understand what atoms are made of, but what's that got to do with the periodic table? Well, what makes an element unique is the number of protons in the atom. We don't really care about the neutrons. And if it's a neutral atom, of course, the number of protons are balanced by the number of electrons. So hydrogen, where are you, hydrogen? That's it. Try to stand up, hydrogen. Okay, so you are the first element, in fact, the most abundant element in the universe. You've got one proton. That's what makes you hydrogen. One proton, one electron for the neutral atom. Sometimes neutrons, but we don't care about those. The next element, on the same row, we go all the way around to here, and we find helium. You have two protons. That's what makes you, you. Excellent. And then we come back over here to periodic table, so you're very good. Lithium, yes, you've got three protons, that's what makes you you, and so on. That's what we do when we go from one element to the next. We increase the number of protons by one and the number of electrons in the neutral atom, and maybe throw in a few neutrons. Now, the question is, though, we've got 118 elements, but we've got literally tens of millions of different compounds. So how can we get such complexity out of just these 118 elements? In fact, in this cup of coffee alone, well, over 2,000 different compounds have been detected so far. So loads of compounds, only 118 elements. Well, there's a nice analogy between letters and words with these elements and their compounds. So I could be saying hundreds of thousands of different words now, but these are all made up of the same 26 letters of the alphabet. Words like I and A are made up with a single letter. There are some words that have two of the same letter. Ah is a type of Hawaiian lava. What a silly word that is. But then there's another Hawaiian word, this is ah, or something like that, which is an insect also found in Hawaii. Now, our elements are the same sort of thing. The letters then correspond to the elements, and there are some elements that just stay by themselves, like these letters. So helium, can you put your card up, please, helium? Where are you? Ah, there you are, good, helium. And neon, and argon, all of you, they just stay by yourselves, just single letters, if you like, single elements. But we have other elements that go around in pairs. Where's nitrogen? Nitrogen, put your card up. Oxygen, fluorine, all of you go around in pairs. Chlorine, you'll go around in pairs as well. So you're around in pairs. And occasionally oxygen, just stand up again, oxygen. So occasionally you have three oxygen atoms that make up a molecule of ozone. Okay, thank you very much, elements there. But most of the periodic table, well, you are loads of these single atoms together, all joined together to form big masses of metal or non-metals or whatever you are, if you're solid. So this would be like a word like going on forever with so many letters we couldn't count them. But that's not how we usually find the elements. How we usually find them is combined with one another to form compounds. So if the letters correspond to our elements, the words that we use, these correspond to different combinations of the elements, these are the compounds. So the elements want to combine with one another to form different molecules. And we're going to try an experiment now to show this, to show the combination of two elements. And this is the element oxygen, one of the elements in the air. Oxygen, where are you again? Show us where you are, please. There's oxygen. And between phosphorus. Phosphorus. Can you stand up, please? Phosphorus. Okay, now, do you know how you were first discovered, phosphorus?
No.
No? Okay, well, we'll give you a bit of a clue. What's your symbol?
P.
P? Any idea? No? Does anyone else know? Okay, there's a chap right at the back there. So where do you think phosphorus was first discovered?
From we.
From we, yes, exactly. Okay, so thank you, phosphorus. You can take a seat now. Well, I've got some urine here. It's only mine, so it's not too bad. Okay, it's all right. Smells quite nice. Would you sniff? Oh, you do? Yeah. Well. It's fine. No, don't worry, it's only apple juice, really. But back in 1669, the German alchemist Hennig Brandt did take his own urine and he heated this up, and this amazing substance came out, and this was phosphorus. So how come phosphorus was discovered so early? Not just because it was disgusting, but also because once you found it, you couldn't miss it. It just screams out to you. Here I am. Okay, well, let's try this. So we've got some phosphorus in this flask here, and I'm just going to let the air into this. We've removed the air and heated up the phosphorus. Watch what happens here. Maybe we can have the lights down just a little bit here. So as soon as the air comes in, it combines with the phosphorus. This is phosphorus reacting with air, and this amazed the alchemists. When they saw this, they were truly stunned. In fact, they were so impressed by this amazing light that the reaction is giving out, they named this element phosphorus, which means the light giver. This discovery was commemorated with a painting by Joseph Wright of Derby. It's on the screen here. Has a really catchy title. It's called The Alchemist, in Search of the Philosopher's Stone, discovers phosphorus and prays for the successful conclusion of his operation, as was the custom of the ancient chemical astrologers. Snappy, but it sort of says what it is, and you can see this amazing look in the alchemist's eyes as he's made this fantastic discovery. This is far brighter than any of the lamps or candles at the time. And I have a description here. This is from a book from 1692, and it describes phosphorus. It says you need to store it under water because it reacts with the air, but it also says here, if the privy parts be therewith rubbed, they will be inflamed and burning a good while after. Now, there's one that you really shouldn't try at home. Please don't go smearing phosphorus on your privy parts. It's not fun. Anyway, but the alchemists made this discovery. They found phosphorus. They knew it was reacting with the air, but they didn't understand fully what was going on because they didn't know what the air was made of. Okay. Chemists now know that it's a mixture of gases and a mixture of different elements that makes up the air. Now, we're going to have a look again at the different gases that are in the air. In fact, first of all, can we have all the elements that are gases? So all the gaseous atoms. Can you stand up, please? So where are all the atoms that are gases? Okay, so we have hydrogen over here. Well, it's a good job there's not too much of you in the air, because that would make it very flammable. So if you sit down, it would all explode if there was too much hydrogen. That wouldn't be very good at all. Who else have we got? Well, we've got nitrogen and oxygen. We know that you're the major components, but then we've also got fluorine and chlorine. Fluorine, chlorine, you're incredibly reactive, which also makes you incredibly toxic. So it's a very good thing that you're not in the air as well. So perhaps you can sit down as well, please. But look where the gases that we do find in the air are. Okay, we've got nitrogen and oxygen, we've seen you, but then we've got all of you sitting here, well, standing here with your white cards. You're the so-called noble gases. Why are you all sitting together? Well, this is not a coincidence. It's because you all have very similar chemical properties, and there's this amazing pattern when we arrange the elements in a certain way that every so often elements with the same chemical properties are found grouped together. So if we just have our periodic tables up, please. So that's it, fantastic, very good. Now we can see these coloured patterns here. What a beautiful display this is, excellent. So all of you with the purple cards here, you're group 1. You're all really reactive metals, you explode with water, really violently, okay? But you all have similar properties, you're all grouped together. If we come over here, all you with the green cards, for instance, you're called the halogens. You're all really poisonous, rather unpleasant substances, but you combine with these over here, with the alkali metals, and you form salts, very violently indeed. Okay, Atti's periodic table. We're going to look, though, at our noble gases. So if everyone sits down, but I'd like the noble gases now to come down to the front. We've got some samples for you. A balloon of you krypton, hold the string and hold it out. Beautiful, okay. Xenon, again, hold the string, and there we are, and then we come, now we have a slight problem with radon, I'm afraid. Radon is incredibly radioactive, so health and safety wouldn't let us give you a balloon full of radon, you'd go home glowing, so we'll just put this on you there. That's great. And ununoctium. I'm afraid ununoctium hasn't even got a name. Okay? And this is because there's so few atoms of ununoctium that were made, or we're not even sure if they were made, that we couldn't fill a balloon full of you. But you've got a balloon anyway. Okay. Yeah. Okay, so Right, now you've all got your balloons, and after a countdown from 3, I'd like you to release your balloons, keep hold of the strings though, and we'll see what happens. Okay, so 3, 2, 1, go. Look at that. Now, what do we see here? Well, we all know that helium balloons float. Okay, so you have got nice light element there, helium. What about this neon? Well, neon, well, it's about the same. If you dropped your string there, okay, so it's about the, keep hold of the string, it's about the same sort of density as air. It's the balloon that's making it sink. Argon is getting pretty, more dense there. Yep, thank you. Krypton is really quite heavy, and xenon, you wouldn't want to go to a party with that, would you? I mean, you'd be dragging this along the floor. It's a very expensive gas. This is probably about £100, this balloon, but yes, it's very heavy indeed. Now, what does this tell us, though? Each of these balloons actually has the same number of atoms, because equal volumes contain the same number of particles. It tells us that the atoms of helium are much lighter than the atoms of xenon, and that's because of all the subatomic particles that make up these atoms. The helium just has 2 protons and 2 neutrons, all the way down to unonoptium. You've got 118 protons and loads of neutrons. Okay, I think you've done fantastically well. Would you like to return to your seats then? We've seen that we've got different densities of these gases. They have different masses, but they also have very similar properties. And each of these elements is a gas, and we've filled these signs up with these gases. We can see that you're all colourless. You're also all odourless gases, which is a good thing. Okay, you don't smell at all, but not very exciting to look at until you pass a few thousand volts through you. Watch what happens then. They all become much prettier. Well, this is the normal neon signs that we see. This sign here is filled with neon gas, but when it gets excited with the electricity there, the electrons are leaping up, and as they come back down, we get this fantastic red colour. Each element has its own unique colour. So we can see then that some of these gases have uses. Neon is used in neon signs. But some of them have even more important uses. And I went to the University of Sheffield to have a look at one of the uses for helium. So what's in this little bag here that I've got then, Jim?
So what you've got in there is essentially a bag with some helium atoms which are magnetically aligned or polarised, and they're contained within the bag. If we were to actually image the bag, you'd see just the boundaries of the bag and the airspace inside the bag filled with the gas and nothing on the outside. And similarly, when you breathe it in, we'll see the gas inside your lungs.
Now the scanner is actually a giant magnet with radio detectors which detect these specially prepared helium atoms as they return to their natural state within this magnet. And this allows Jim to build up a picture of where the gases are in my lungs.
So there are your scans, yeah?
Those are my lungs.
So there's your bronchus, your trachea, and your 2 bronchi, and the feeding bronchi coming off the bronchus. These are your blood vessels.
So the amazing thing about this is that we're only seeing the air inside my lungs, aren't we?
Exactly, yeah. You're just visualising the airspaces there. So
it's very, very exciting to be looking at my own lungs. It's nice to know that they're not too bad, even though I know I've got a bit of a cough at the moment, but nonetheless, they're reasonably healthy. They look pretty healthy. Yeah, that's all right. Yeah. So this is pretty cutting-edge science here. We're actually using this form of helium, helium-3, to image the workings, how a lung works. And actually on the screen we can see here, these are 2 lungs. This is a lung of a patient that has asthma on the left-hand side here. You can see some black regions. But after they've taken their inhaler, the lungs have opened up, the airways have opened up, and the helium has got into those regions, and we can see all the places where the air is now reaching. So this just shows the medicine in action. Okay, now, it's not just helium that has exciting properties. If we go right the way down to the bottom of the periodic table here, the heavy stable element xenon, this has some truly remarkable properties as well. We have a tank here, we've filled this with some xenon, I understand. There's some xenon in there, so there's a little xenon. So we just keep putting a little bit more in there. And I have a very delicate, very fragile foil boat. And I'm going to see if we can actually balance this, if we can float this on the xenon in this tank. Try the washer one more time. We should try this one first, I think. Yeah, try our new boat. Let's just slide this over. And try our new boat. Ah, that's it. Look at that. That really is floating on the xenon. There are no strings. It's a little bit fragile here. I think I need a volunteer to just come and very carefully help me add some weight into this. We'll have somebody from yes, right on the end. Yes, would you like to come down? Yes, okay, thank you. Okay, thank you very much. Give it a round of applause. Let's come on here. Okay, I'm just trying to keep my boat level here. I'll just add a little bit more xenon. Now, so what's your name, please? Bethany. Excellent. Now, you are going to be probably the first person in the world ever to try this. We haven't even practiced this. Have a look at this. What do you think this is? How do you hold it?
Foil.
It's foil. Does it feel like normal foil?
No.
No, it feels a bit strange, doesn't it? That's because it's pure solid gold. All right? This is pure solid gold. So let's just screw it up a little bit, and I'd like you to put this in here. Okay? See if you can just put it in that corner. That corner's a little bit unstable at the moment. That's it. That's that. Oh, look at that. Now you have made this thing floating perfectly. That's pretty amazing. Add some more. Will it sink? Will you sink it? Not quite. Oh, there it goes. Fantastic. That's it. Thank you very much. Excellent. Okay. Xenon is very dense, and I'm very pleased that worked. But it also has some really remarkable properties that can be used in medicine. Now, while I was at the University of Sheffield, we took a chance to experience what it's like to breathe in some xenon, and it has very strange effects on the body, but it can be very useful as well. So let's just see what happens here.
You take a deep breath in, Peter.
So,
breathe out. Deep breath in. Yeah, and then I'll breathe from the bag. Okay. Breathe in, 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 breathe in. Okay, and hold your breath. Be interesting if you talk as you breathe out. We'll see if we can hear the...
That's amazing. I feel really relaxed. And I can hear that my voice has changed. It has gone quite deep now. But I feel very happy and relaxed and calm. Oh, it's wearing off now. Wow. So that's xenon. These individual atoms of xenon interacting with my brain in some way, isn't it? So it's going into my bloodstream and interacting with my brain and making me feel slightly lightheaded. And that's at higher concentrations that acts as an anaesthetic, and I would just pass out. Is that right?
People do use it as an anaesthetic in a clinical setting, but clearly at higher concentrations than these. And if we'd have retuned the scanner slightly, we'd have actually seen the xenon atoms dissolving in your blood as well. That's where we're going with this at the moment. We'd love to actually be able to pick up the xenon dissolved in the brain and image the xenon in the brain. That might give us some insight into how these anaesthetics are actually working in the neural system. So,
incredible.
Yeah.
Now, that was certainly very strange when I was breathing in this gas. And the latest research that Jim is doing allows the individual atoms of xenon to be followed around the brain even. Now, I'd like you to welcome three incredibly important guests to the RI. Would you please welcome Dave, Sarah and Riley Joyce. Thank you. Oh, he's very shy in front of the cameras here. Okay, now then, I was wondering, could you tell me your middle name? What's your full name? Can you tell me your full name? Bit shy. He's a bit shy. Okay, what is his full name then, please?
So it's Riley Xenon Joyce.
Riley Xenon Joyce. Okay, now I think this is great. I would love to have an element for a middle name, I must say. But so why is Riley's middle name Xenon then?
Well, Riley was the first baby in the world to receive Xenon, and he received it at St Michael's in Bristol. Due to when he was born, he didn't have a pulse, and had to resuscitate him, so he was starved of oxygen.
And this could have caused complications if he didn't get this treatment at the time. So this was acting as an anaesthetic, so this was right. Was it just sort of gently put him to sleep and just allowed the metabolism to slow down?
Yeah, give him his brain sort of time to sort of recover, and he had it alongside the head cooling treatment,
right, which
works sort of along the same principle.
Well, I must say that he's very shy at the moment in front of everybody, but earlier he was running around all over the place, so he's clearly perfectly healthy now, isn't he? Is that right?
He is. March this year he had his 2-year checkup, and he was discharged as a perfectly normal, healthy child. When he was born, he was given 50% chance of having permanent brain damage. So to come from there to where we are now is incredible.
That is absolutely fantastic. So would you please thank them for coming in? If we just have our periodic table up for a moment, have our periodic table up. We've seen that we have our noble gases here. You're all individual atoms. You don't really want to combine with the others, but this isn't the same throughout the periodic table as a whole. We're trying to understand what makes some of the gases in the air so special, but in order to understand these, how they're bonding with each other, we need to look across the periodic table as a whole. I have a sample of one of the elements here. This is the element potassium. So potassium, can you stand up, potassium? There you are. So you're in this first group, in the same group as lithium, sodium, potassium. Very good, thank you very much. You're a solid. And in here we have the solid potassium. Potassium is a metal, and we've got this in the flask. Atties periodic table. Thank you. Cards down, very good. We've got a little piece of the potassium here. And we've taken the air out of this flask. I'm just going to gently warm the flask up. So potassium is a metal. The potassium atoms want to bond to each other, but they don't bond to each other very tightly. So it is a solid, though. It's not a gas like our noble gases, but watch what happens if I just warm it up rather gently. Potassium is, oh, look at that. What's happened here, all of the potassium atoms have separated from each other and given this fantastic coating over the inside. In fact, we made an instant Christmas bauble, which is great. But this is a Christmas bauble coated with potassium, which is probably not so great. But anyway, very, very beautiful. But we didn't need to put a lot of energy in to pull those apart. How can we understand this? Well, we're going to go back to, if we have a periodic table back up, we're going to go back to the top element in the second row. This is lithium, and we're going to move around our periodic table from lithium through beryllium, all the way boron, carbon, nitrogen, oxygen, fluorine, neon, and see how the bonding changes. So we have our elements lined up here, and you bring in down electrons. So we have the first two lithiums, please. Could you come down to the front, please? And you're going to bring some electrons with you. So these are our yellow electrons, and could you put them in the energy level here, please? Okay, that's it, put them in there, and if you return to your seats, that's great, thank you very much. Now what's happened here, as the electrons have gone into this region here, into these shelves here, these have pulled the atoms together. And this is because these negatively charged electrons are helping pull the nuclei together when they're concentrated in between the two atoms here. We have our next elements. We have beryllium. Could you come down to the front, please? Now, in beryllium, we see on the screen here, the bonds are much stronger. Let's see why this is. We add your electron here. That's it. These are moving the atoms close together. There's even stronger still. Okay, so beryllium has two electrons, creates a stronger bond now. Lithium, beryllium. The beryllium atoms are held more tightly. Okay, boron. Boron on the screen here, we have 3 electrons. Can you come down, please, boron? You've got one more electron here than the beryllium had. So you're going to add your electrons. Can you add your electrons in here as well? And again, these have gone into, oh, that really did move there. Yes, that was pretty good. So you've got a very strong bond now for the boron, much stronger than the beryllium, very tightly held. We've got 3 electrons bonding these boron atoms together. Can we have carbons now, please? Okay, and that last one. Okay, so the atoms move closer together. Thank you very much, carbons. We've got some very strong bonds indeed now. In fact, carbon there has requires the most energy of all of the elements to try and rip them apart. If we were trying to remove the same number of atoms apart, we need more energy for carbon than any other. This makes carbon incredibly strong. And I have a sample of carbon here to show you and demonstrate this. This is a diamond. We can see this here. This is just a real diamond. Very, very strong because of these strong bonds. Oh, nearly dropped it there. But it also is incredibly hard. So hard, in fact, that I can actually cut this glass. The glass is incredibly hard, of course, but diamond is even stronger because of the strong bonds between the carbon atoms. So, well, it's definitely cut into the glass. In fact, it looks like it's pretty deep. All right, so cut down this crack where it's been scored with the glass there. So diamond, incredibly strong because of all these bonding electrons keeping the carbon atoms together. Okay, but we've still got further to go along our periodic table. We've gone to carbon, we're going to keep on going. So nitrogens, you have 5 electrons in total. So let's see where these have to go. Now we've run out of room here. You're going to have to put your electrons in these ones. So this is a slightly different thing going on here. Would you put your electrons in here? That's great. And these actually now are concentrated outside of the middle. And these electrons are pulling the atoms further apart again. In fact, these do not help the bonding. These are called anti-bonding levels. Thank you very much, nitrogens. Okay, we have our next element. This is oxygen. Let's see what happens as we keep going. Add in another electron. So oxygens, you have to put yours in the level here. And again, these are in these anti-bonding levels, pulling our atoms apart. Well, so oxygen is a weaker bond than nitrogen. Well, let's go to our next atom. We've got 2 fluorines coming along. Let's see what happens when you get together. Okay, add them in. That's great. And again, a very weak bond now. It's pulled further apart. Fluorine has 1 more electron, weakens the bond here, and the fluorines are really weakly held together. And this is one of the reasons that makes fluorine so incredibly reactive. It's because of these weak bonds. Finally, we have our last elements, neon. So neon has 8 outermost electrons, so it's got 1 more than the fluorines had. Let's see where these have to go in the remaining level here. So if you add your electrons into these last anti-bonding levels, and it pulls the atoms completely apart. So this means the atoms do not bond to each other. Thank you very much indeed for your help there. Thank you very much. So, if we just see our periodic table again, we just have you up last time, that's great, thank you very much. And we're looking then at this one's over here, we see carbon, very, very strong bonds, nitrogen, not as strong as carbon, but still pretty strong, fluorine, very weak bonds, neon not bonded at all, but oxygen, you have about the right strength, you're still reactive, because the bonds aren't too incredibly strong between the oxygen atoms, makes you very, very reactive indeed. Oxygen, you really are the elixir of life. It's you that keeps us all alive. I'm going to demonstrate this now. So at ease, periodic table, thank you. So I have some breakfast cereal here. This is just normal breakfast cereal. And just going to put some in the bowl. So this is just the sort of thing that you would normally do. But now instead of adding my milk, I'm going to add some liquid oxygen. So this is not the sort of thing that you normally do. Now we've cooled the oxygen down. So this is oxygen gas that's being cooled down. It has this beautiful blue colour. I'm just going to pour this onto our Rice Krispies. Okay, now I'm also going to add a light. Let's put my goggles on. This is also something that you don't normally do. An incredible amount of energy is released there. this is as the Rice Krispies, the breakfast cereal here, as our breakfast cereal combines with the oxygen from the air. And believe it or not, this is actually what happens inside our bodies. Not quite like this, I mean we don't have flames coming out of our ears, but nonetheless it is the reaction between our breakfast cereal and the oxygen that we're breathing in that gives us the energy to stay alive. And we have Laura here to demonstrate this. She's been specially trained in breathing with this rather delicate apparatus here. Okay, would you like to put this on? Now, what's happening here? Laura is breathing in, so if you breathe in, that's it, breathing in normal air, and it's coming in through here, bubbling through this solution. In the flask here, we have something called lime water. And then Laura's breathing out through this one, so the out air is coming out through here. Now, lime water reacts with carbon dioxide. There's very little carbon dioxide in the air, and so there's no change taking place here. When lime water reacts with carbon dioxide, it turns cloudy due to the formation of calcium carbonate. No calcium carbonate forming here, but in the out, well, we can begin to see already, so keep breathing, very good, you're breathing beautifully there. Okay, in the out, we can begin to see that it is going cloudy, and this is because inside Laura, well, it is the same reaction that we saw taking place there. The breakfast cereal that Laura had this morning is reacting with the oxygen that she's breathing in. It's releasing a lot of energy, and that's keeping Laura alive, but she's breathing out carbon dioxide that's formed during this process as the oxygen reacts with the fuel to produce carbon dioxide. Thank you very much. Give Laura a round of applause for where this was. So, oxygen is incredibly important just to stay alive. But we've seen that there's only 21% of oxygen in the air. So wouldn't it be better if there was much more oxygen in the air? Well, probably not. I'm going to demonstrate this now with the help of my volunteer here, Sausage Man. Okay. Now, Sausage Man is made up of the same sort of things that I'm made up of. He's made up of meat, of course. And I'm just going to, we've connected him to a heating wire. I'm just going to turn up this heating wire here. So there we are, the heating wire is, just turn it on a very low voltage there. It's just beginning to heat up. Now, it's not really causing too much of a problem, but watch what happens if I increase the amount of oxygen in the air. Now, again, we're going to use the liquid oxygen to do this. It's just to provide a lot of oxygen gas in the environment. And so he's just with the heating coil there. Is anything beginning to happen? His leg's smoking a bit as the wire's just heating. So this is like you're on a different planet and there's a lot of oxygen on the planet here. You accidentally lean against the cooker and look what's happening here. Poor Sausage Man is now in flames. And he's gone up rather drastically here. This is because of the increased oxygen in his environment. So yes, of course, we do need oxygen to stay alive. It does provide us with our energy, but too much would definitely be a bad thing. I need to put out our Sausage Man. I think it might be very difficult to put him out since there's so much oxygen in there. Let's try. We've got some tomato ketchup here. It's wow. Oh, it leaks as well. Great. Somebody didn't put the top on properly. There we are. We've put him out. Oops. What a mess. Okay. So you get the idea that too much oxygen would certainly be bad for us. But I mean, on a serious note, it's incredibly difficult to put out a forest fire. Okay, these are incredibly difficult to put out even with just 21% oxygen. If it was 100% oxygen, there would be no chance. So 21% of the air is made up of oxygen, and this is how much we need to breathe. But what happens if you reduce the amount? Can we still stay alive? Well, I went to a place just outside Cambridge where they've reduced the amount of oxygen in their rooms there from 21% down to 15%. And they say that things just can't burn in this environment. Well, let's see what happens.
Can I have a fire?
Yes.
Can I set fire to your newspaper?
I've got a newspaper here, and you try to light my newspaper.
Okay.
All right? See if it works.
So shall I use the lighter or the...
let's try lighter. Use the lighter.
I'll try the lighter
Yeah.
first of all, okay.
Oh, empty?
I don't think it's very
Try mine if yours is empty.
This is a new one, is it? Okay.
Okay, does it work?
Matches.
Matches, okay.
Ah, this is better.
Okay, okay, try again.
Of course, the matches are still lighting because they have their own oxygen built in here, and that's what's allowing them to strike. But there's not enough oxygen to allow your newspaper or the match to actually burn.
You're right.
It's only the match head here with its
Absolutely
oxygen
correct.
there.
The newspaper could not burn by itself. Impossible.
And of course, we can breathe fine in here. It doesn't affect us.
It doesn't affect us at all. We could live in here forever.
Very impressive.
We've come outside to try a slightly larger scale version of the lighter. The lighter couldn't start a fire in the room because it didn't bring any oxygen with it, and there wasn't enough oxygen in the room itself. So this is petrol. I've soaked this torch here in petrol. It should light nice and easily. Yes, look at that. So this is burning rather well. The question is, will this go out in the room? Well, let's find out.
And the fire has instantly gone out. There really just isn't enough oxygen in this room to allow my torch here to carry on burning, but there is enough for me to carry on living, so that's pretty good and I'm happy.
So this fire prevention system works by decreasing the amount of oxygen and increasing the amount of nitrogen. And nitrogen is a very important component of the air because it's so inert, because of these very strong bonds. So we're now going to look at some of the properties of this inert gas, nitrogen. And this is one of the components in many explosives, such as this nitroglycerin here. This is a very dangerous explosive. In fact, Alfred Nobel earned his money in trying to work out how to make this more stable. Now I need to put on some special kit here, some protective clothing and some ear protectors. Okay. And I'm going to add a drop of nitroglycerin to the filter paper. Now then, adding a drop of nitroglycerin, there we are, that's it. And I think I'll just remove this nitroglycerin from here. I don't want to be too close when this goes off. So I'll hand this to Mark, thank you. Right. Now, the nitroglycerin contains a lot of nitrogen locked up into its chemical composition, and it's the sudden release of this that gives it its explosive power. That really was quite violent, the sudden release of that nitrogen gas. And that's what makes an explosive explosive. Most of them contain nitrogen built in. But remarkably, this reaction, this explosive release of nitrogen gas, has been used to save thousands of lives. And for this, well, I need a car. We've got a car there, please, Chris. Okay, well, it's not exactly a real car, but it is a real steering wheel. Okay, so this contains a compound with nitrogen in it. It's nitrogen combined with sodium. Could we just have our periodic table up for a second, please? So we have nitrogen over here combined with sodium over here, but it's the formation of our very, very strong nitrogen-nitrogen bonds that leads to the rapid inflation of this airbag. Now, I need a volunteer from the audience for this, please. Who should we have? Yes, would you like to come down the front? Okay, thank you very much. So, just stand all the way over here, and your name is?
Fred.
Fred, okay, Fred. Now, you're going to trigger this airbag. So if I just take this from Chris, is this primed? I'm just going to make sure it's all okay to trigger. Okay, thank you very much. Now, if you stand here, just right over here, he's very keen to get a hand under the trigger here. Okay, now, so we're going to count down from 3 there, okay? So if you hold this, don't press the button yet, okay? Now, when we've counted down, I want you to press the button, but don't blink, okay? If you blink, you'll miss this. It's a very quick reaction. Okay, so 3, 2, 1. Oh, there we are. Okay, thank you very much indeed. Give a round of applause for Fred. So this airbag works here because the nitrogen really wants to bond to itself to form these nitrogen molecules, and it's this explosive release of nitrogen that inflates the airbag so quickly. We can see this here in slow motion. So when the crash test dummy hits the bag, this bag is actually deflating. The air is coming out of this. Okay, but it needs to be released so quickly, that's why an explosive is needed. So nitrogen here, saving lives. But actually, nitrogen is vital for life. We couldn't live without it. Every protein in every cell in our body is made up of amino acids. And every one of these amino acids contains nitrogen. So somehow we need to take the nitrogen from the air and get it to combine with other elements so we can form compounds that are useful to us. Now, plants have learnt how to do this over millions of years, but it took chemists a long time to do this. And the first way this was achieved was by emulating nature, a process in nature where nitrogen and oxygen are beginning to react. During this electrical storm, the lightning here is providing sufficient energy to split apart these molecules, and this can allow nitrogen and oxygen to recombine. We're going to try and do this in the lecture now. And I have, this is what every mad scientist should have. It's a Jacob's ladder. And here we see it switched on. So what we're doing here is passing thousands of volts between these two electrodes, and this is causing the molecules in the air to be ripped apart, ripping their electrons out. This heats up the air just above it, making it easier to pass the electric current through that, which is why this thing is gradually rising. But how will we know if there is any chemical reaction taking place here? Well, we're going to keep an eye on this, and what we're going to be looking for is signs of a reaction. We should see a colour change. Now, I can demonstrate the colour change that we're going to see. I have 2 flasks here. This contains a compound called nitric oxide. This is just air. But when the two come together, we form a new compound that we can see that isn't colourless. There we are. And this is the gas nitrogen dioxide. So this is what we're looking for in our Jacob's ladder. So the nitrogen, if it combines with the oxygen, we may be able to see this coloured gas, nitrogen dioxide. Okay, so we'll keep an eye on the tube there. It just contains air. Okay, if we can I'll just get rid of that. But this isn't really real lightning. This is only a very small spark here. We can maybe begin to see hints of some colour change, but we'll keep an eye. We need a bigger spark. We need something to produce, well, about 1 million volts. And this is what this is for. This is a Tesla coil then, and it can generate 1 million volts. We've had some problems with this bit of kit. It basically fries all the cameras, all the electrics, all the lights. So this really should give us some rather impressive lightning. Now, I must ask everyone just to remain in your seats for this demonstration. Let's see how we go. That really is quite nerve-wracking, I must say. And this, what we are seeing here, with all that energy, it was causing the nitrogen molecules and the oxygen molecules to be ripped apart, and then they recombine to form maybe nitrogen dioxide, and that's what we can see, this brown colour here now in our Jacob's ladder. And we can also form molecules of ozone, that's 3 oxygen atoms together. So what have we learnt here? We've learnt that the air is more complicated than we ever thought. The alchemists thought it was made up of just one element, but they were wrong. It's made up of a number of different elements of nitrogen and oxygen. We've seen how important they are to our lives. Without the oxygen, we'd all be dead, but with too much, we couldn't survive either. But we've also seen how the very rare gases, the noble gases, can be used to save lives in hospitals. Now, the alchemists spent their lives trying to master the elements, but they only scratched the surface. They might have been able to play with fire, but they couldn't control it or understand what it was made of, nor could they pick out the elements from the air and use them to make the world a better place. This is where the modern alchemist takes over. Join us in the next lecture, where we'll investigate how a glass of water contains the remnants of the most violent reactions in the world. Good night.
Brand new drama coming up here on BBC HD Next this evening, with the compelling story of Tippi Hedren and Alfred Hitchcock in The Girl next.